Oh, g'day guys, it's Mr. Bennett here. I'm just going to go through the introduction to the matrices topic, so just follow through what we do here. So the first thing we're going to do when we start looking at matrices is we're going to be investigating the three different types of connectivity, the dominance and the costing matrices. And we'll also be looking at an application called a transition matrices or a Markov matrices. These are really useful when you're looking at predicting what's going to happen down the track, so looking at long-term trends. We'll be looking at an example of cryptography and then also the business inventory as another example where you might use big matrices. So the idea there will be just putting into context why we might use matrices. So the sort of things that you're going to need to know is the basic skills of how to add and multiply matrices together. You're going to need to be able to do the three different types of matrices that we talked about before. You'll need to do matrices algebra. Right? You need to be able to find inverse matrices for a 2x2 and a 3x3 matrix, and do the same thing for determinants. Okay, you'll need to actually be able to calculate those for 2x2s and 3x3s, and obviously you need to know how to do a transition matrix. Now they are very typical sort of questions that you'll see in exams. So just some basic information which you would have covered last year in year 11. So obviously we have rows going acrossways, we have our columns coming down. So this matrix here has 3 rows, 3 columns, so it's a 3x3 matrix. And if you look at the positions, okay, we would say this position over here is row 1, column 3, right, or row 3, column 2. Right, so they're the positions in that particular matrix. So when you're adding or timesing by a scalar, so what you have to do when you're timing by a scalar is simply times every term in the matrix by that particular value. So in this case we're doing 4 by 2, 8, 4 by 5 is 20, 4 by minus 3 is negative 12. I think you can sort of follow that. The other thing is, for adding matrices, what you're doing is you're adding like terms. Okay, so you're adding row 1, column 1 with row 1, column 1 for both matrices. So 2 plus 7 is 9, negative 3 plus 4 is going to give you 1. Alright, so you're adding the like term in the matrix. In other words, have to be, the same type of matrix to add them together. And obviously when you're taking the same process, so it'd be like 2 take 7 will give you negative 5. So it's again the same like term in both matrices there. Okay, so fairly basic stuff that you would have seen before. Now when we're multiplying matrices together, we simply times the row by the column. Alright, so this matrix here is a 2 by 3 matrix. This matrix here is a 3 by 2. So therefore, when we times that together, we should get a 2 by 2 matrix at the end. Alright? So, if you look at what we're doing there, we're going to get 3 times 7, 4 times 1, 5 times negative 3. So that's going to give you 21 plus 4 minus 15 will give you an ultimate value of 10. Alright, so you do that. Obviously, row 1, column 2 will give me position 1, 2. Alright, and if I have row 2, column 1, that will give me position row 2, column 1, and then row 2, column 2 gives me position 2, 2 in the matrix. Alright, so I think you can follow through the algebra there, what we're doing. Now, obviously, we can do this on our calculator, which we will obviously have to be able to do. Alright, so here's a very, very basic example. So, you wouldn't need to work it out like this, you could just do it in your head. But if you had the number of soft drink cans, the number of chocolate bars, the number of ice creams by their price, you could simply do that matrix by that matrix in there, and that would tell you how much they actually cost. Alright, so the cost for 3 cans, 4 bars and 2 ice creams is $9.90. Alright, so a very simple example. So here's some matrix algebra that you need to know, and a bit like normal numbers and normal algebra, sort of things actually hopefully make sense. So this first dot point is saying it doesn't really matter which way you add matrices together. Right, it actually doesn't make any difference. And again, the same thing in the second dot point is, A plus B's plus C is the same as A plus B plus C with the brackets in there. Right? If you add 0 to a matrix like you would to a number, it doesn't change things. The thing that does make a difference is the way you order that you times matrices. So A times by B is not necessarily equal to B times by A. Alright? If you times a matrix by 0, like you would times a number by 0, that's going to give you an answer of 0. This next one is using the distributive law, and that would still work for matrices as well. A times B plus C is going to be the same as A times B plus A times C. And then obviously A times the inverse, the identity matrix. Now the identity matrices has 1s on the diagonal. Okay, so A times I or equals I times A, which is simply equal to A. And if you times a matrix by its inverse, doesn't matter which way you do it, you're going to get the identity matrix. If we have minus there, we just times a minus through both things. Now if we have to solve for x for this particular equation, first step would be to divide the b by a half. Alright, so it's a half b, and then what we do is we bring a across. So obviously if you want to bring it across the other side, you have to make it minus a. So the algebra for matrices is very much the same as algebra for anything else. Right, here's a very classic sort of question. We get something like this one over here where we have to square that out. So we would use FOIL to do that. Eventually we'd get down to the bottom here where we've got something like a squared plus 4a plus 4i. That would allow us to then simply express the answer like that. If we're given something like this one over here where a squared is equal to 2a plus 3i, and we have to find a cubed and a4, well, we know that a cubed equals a times by a squared, so you'd expand that bracket out using the distributive law, and then you would substitute where you find the a squared for this one here. But this is the sort of question that you'll have to be able to do, and we'll go through those. Alright, costing matricing. If we're looking at, I'll just go back to the previous slide, just so you can see what we're doing. So here's some information in terms of beef, chicken and that for different days. Alright, so this is what a shop sells in terms of that. Obviously when you're doing these, it's really important that you keep your big matrix in one format, and we can arrange that information into either a row or a column matrix. Right, so this is the price for the different types of pies for different days. So obviously if I times that by that, it's going to tell me how much money I make per day for each of the different pies. Alright, now if we're going to go into a graphics calculator, you need to press your matrices button and you'll see a menu appear like this. Now if you want to edit a particular value, then all you simply do is go to edit, select the matrix that you want. You will type in the dimensions of the matrix, and then it's just a matter of typing in the values. Right? So obviously when you complete a calculation on the calculator, and we'll go through this in class, is what you need to do here is you need to select the matrices you want to do something with. So if I've got these exactly the same dimensions, then I can add the two together. So you simply do it on your calculator. But you do also need to be able to times this by hand, and I'll talk about examples when you need to do that. Now the inverse matricing will be something that we'll look at again, and I don't want to go through a lot of detail because we'll go through this in class. That's the sort of working out you need to do there, and I'll include this PowerPoint in your file so you can actually have a look at this PowerPoint yourself. The reason why we might use the inverse matrix is it'll allow us to solve for x and y if this is the case. So we go through the algebra of timesing by the inverse, we times that at the front both sides, then we get I times by x, so therefore x is the thing over here, and we can use our inverse matrix to do this without using our calculator. Right. Now the determinant of a matrix will determine whether an inverse exists. So if the determinant's not equal to 0, then the inverse matrix exists. Alright, so keep that in mind. Alright, so the determinant is simply the diagonal, so 2 times 4, take 3 times by 1, or 1 times by 3. So, and if you've got a 3 by 3 determinant, it's just a little bit more complicated, but it's a really easy process, and we'll go through that in class again. So this is about learning about what you need to do. Looking at an example of a transition matrix, here's basically just a fairly simple one where we've got a computer company. We've got ACE computers. So what this really means, and the thing is, 80% of the people who buy ACE this time will buy ACE next time. Okay, 30% of the people who buy ACE this time will buy the other competitor next time. Alright, so we can sort of go through that sort of calculation there. Alright, so if we square it, what that really means we're doing is looking at in 2 times, and not next buy but the buy after. Alright, so this is the market share after buying 2 computers. This would be the market share after buying 3 computers, market share after buying 100 computers. And that's pretty well the steady state. So it says that ACE computers would have 60% of the market and the competitors would have 40% of the market. Now, if you're not happy with that, then you would need to do some advertising or business modelling, and you could actually change maybe that percentage. Here's another example here. Right, fitness of players in the AFL side. So the status of this week and the status of next week. So another classic example of the players this week who are getting treatment. Right, we would know that 8%, which is this one here, will be certainly not be able to play next week. They can't play. So but that's sort of the set out that you'll need to do when you're doing this thing here. You sort of say of the people who are fully fit this week, 88% of them will be fully fit next week. Of the people who cannot play this week, 42% of them are getting treatment. Or of the people who are getting treatment this week, 17% will be getting treatment next week. Alright, get the idea? How you actually read that transition matrix. So that sort of goes through what we're going to be doing in this topic. Gives you a bit of an idea about what we're looking at. The only other thing that we will be doing is also looking at row operations as well. And that takes probably a couple of weeks of the program. So we'll get into that in the next video. We'll get into actually doing some work.